Good morning, everyone. My name is Daniele Colapinto, and I'm a PhD student at the Polytechnic University of Bari in Italy, and a technical expert at Pablo Poliba, that is the Digital Fabrication Technology Center of Polytechnic University of Bari. And today I will present a research experience focused on the relationship between art and construction, digital fabrication, and modular structural system. And the aim of our laboratory is to experiment with new digital fabrication technology to teach them in order to promote digital literacy and to use them for prototyping. Pablo Poliba works as a place where research, education, and experimentation come together. We use technologies such as 3D printing, robotic fabrication, laser cutting, parametric modeling, and computational design. For us, digital fabrication is not only a tool for producing objects, but it is a way to rethink the relationship between material, geometry, construction process, and architectural performance. All our research activities start from one main question. Is it possible to imagine a scenario in which tradition becomes the starting point for innovation in architectural form and construction processes? And we don't consider tradition as something fixed or nostalgic. On the contrary, we see it as a technical ship made of material knowledge, structural intelligence, climatic adaptation, and constructive logic. The goal so is therefore not to reproduce traditional forms, but to understand their principle and reinterpret them through contemporary design and fabrication tools. Here we can see some previous research project developed within this approach. These studies take inspiration from the Navian Vault, Wine Tower, and classic architecture elements. Each reference is used not as a formal model to copy, but as a system to constructive principles. The Navian Vault, for example, is relevant because it allows vaulted construction without centering, when the towers combine architectural form and environmental performance, and classical architecture offer example of modularity, proportion, and tectonic articulation. These principles have been tested through different additive manufacturing processes, with viscous ceramic based materials and with plastic materials. Within this research framework, how art plays a central role. Art and construction is one of the oldest building tradition, but today it is also the subject of a renewed international research. Many laboratories and universities are investigating how earth-based material can be combined with digital fabrication technologies, and this interest is connected to the environmental qualities of Earth: low embodied energy, local availability, recyclability, and compatibility with low impact on construction processes. Looking at traditional art and technique, we can identify three main values. Adobe construction is based on modularity. It uses repeated units that can be assembled to create walls and architectural volumes. Cob construction is based on plasticity. It allows the creation of continuous, organic, and adaptable forms. Waterland Daub or Toshi introduces the principle of reinforcement. In this technique, an earth matrix works together with a vegetal framework, improving resistance to bending and tensile stresses. Our research tries to reinterpret these three values: modularity, organic form, and internal reinforcement, and to translate this principle into a contemporary design strategy, we use the concept of spatial tessellation. Spatial tessellation is based on the repetition of a single geometric unit in three-dimensional space. This unit can be understood as an atom for aggregation with other identical elements. It can occupy more complex volumes, and this approach allows us to connect traditional modular construction with computational design. The module is repeated, but its aggregation can generate non-standard, articulated, or organic geometries. The selected module is the truncated octahedron, and the truncated octahedron is a space-filling polyhedron, and this means that it can completely fill a three-dimensional volume without leaving empty spaces between the elements. This property is very important from a constructive point of view because it allows the creation of continuous masses through the aggregation of discrete units. In our research, the truncated octahedron so becomes a interpretation of the traditional Herten block because it's still modular, but it's still no longer limited to the rectangular logic of the brick. By combining the same module in different way, it is possible to generate different object and spatial configuration. The final form doesn't depend on the design of many different pieces, but on the aggregation of one repeated component. This means that this system combines standardization and variation. The model remains the same, but the final geometry can change according to the aggregation logic. And through parametric modeling, we can control this aggregation, test different configuration, and verify the compatibility between the elements. A key development of the module is the introduction of perforation through the hexagonal faces, and this perforation creates an internal network of linear voids. And when the modules are assembled, voids align and generate continuous channel inside the structure. This network has two functions. First, it allows the casting of a more resistant earth-based mixture, creating an internal stiffening system. And second, it allows the insertion of bamboo strips, which provides tensile reinforcement. In this way, the system works as a composite structure. The Artem module provides mass and compressive behavior, while the bamboo and the internal mortar improve continuity and resistance to bending. The experimental phases started with the production of 3D printed formworks in PLA. Each formwork is composed of a top part, a bottom part, and cylindrical inserts used to create the internal channel. The use of 3D printed formworks made it possible to produce a complex geometry with a repeatable process, and it also create a direct connection between digital modeling and art and construction. So the formworks therefore become a bridge between computation design and material experimentation. The next step was the preparation of material, and the mixture was composed of soil, sand, straw, and water. Each component has a specific role. The soil works as a binding matrix, so the sand reduces shrinkage and improves dimension stability. The straw acts as a vegetal fiber, limiting cracking during drying and improving cohesion. And this phase is essential because the performance of the final component depends not only on geometry but also on the composition and workability of material. So after preparing the dry component, water was added to obtain a workable mixture. The consistency had to be carefully controlled, and the mixture needed to be plastic enough to fill the formwork, but also stable enough to avoid excessive deformation and shrinkage. So this is one of the main challenges that when working with raw earth and more generally with viscous material. For this reason, the experiment was not only about producing a final object, but also understanding the relationship between material behavior, fabrication processes, and geometry accuracy. The mixer was then placed inside the formwork progressively. The filling process was carried out in layers in order to improve compaction and reduce internal voids. During this phase, the cylindrical inserts remain inside the formwork, preserving the channel that will later host the reinforcement system. This step show the hybrid nature of the process. The geometry is digitally controlled, but the material is prepared and compacted manually according to the logic of a traditional earthwork construction. Once the elements were dried and molded, the blocks were assembled, and this stage so the internal channel became visible and usable, and bamboo strips were inserted from the aligned wall bodies connecting the different modules. And the bamboo reinforcement is very important because raw earth performs well in compression but poorly in tension, and the bamboo so helps the system respond to tensile and bending stresses. It also improves the connection between the blocks, avoiding the behavior of a simple dry stack assembly. The next step was the casting of a stiffening mortar inside the internal channel. This operation creates a continuous structural network within the aggregation of modules. The mortar fills the voids, surrounds the bamboo strips, and connects the blocks from on the inside. As a result, the system becomes more rigid and compact. This phase is fundamental because it transforms a discrete modular assembly into a more integrated structural body where the single elements cooperate through the internal reinforcement network. Finally, the same material was used to create the upper finishing layer. This layer has both a functional and a structural role. Functionally, it creates a continuous surface that can be used as a seat or support plane. Structurally, it helps keep the module compact and improves the overall behavior of the prototype. The finishing layer also mediates between two different logic, the discrete logic of modules and the continuous surface required by use. Here we can see the final prototype, a small bench produced through this process. Although the object is modest in scale, it allowed use to test the entire workflow, and the prototype shows that traditional airframe principles can be reinterpreted through digital fabrication without losing their constructive identity. And of course, the research is still open. Further developments will concern mechanical testing, durability, water protection, scalability, and optimization of the fabrication process. However, the experiment suggests a possible direction using digital technologies not simply to produce new shapes but to reactivate traditional construction knowledge through the new design methods. Thank you for your attention.